Hello everyone, welcome to Week-13 live session for NPTEL's Introduction to Semiconductor Devices course. I am Om Maheshwari and today we will go through the course summary. So this is an extra session that I'm taking to discuss some of your doubts or just go through the overview of what we have learned in the course and what are some important topics in it. So let us first look at the course outline. So in the course outline, we first started in week 1 with semiconductors in daily life. And we looked at material properties, energy levels in atoms, band diagram, band gap and material classification, electrons, holes, and effective mass. So if we look at this week's uh, if we look at this week's live session notes, so mainly we were looking at the de Broglie hypothesis, matter exhibits wave-like behavior, and uh, lambda is equals to h upon p, this relation. So determining which of the following objects has smallest wavelength or same velocity. So these kind of analysis, then the radius of the orbit is the energy levels occupied by electrons are quantized. So 2 pi r equals to n lambda, where n is this integer and lambda is the de Broglie's wavelength again. Then we looked at the Schrodinger's equation and a particle moving in a free space where energy is s square k square by 2n. So this is the derivation for it. And some questions on the lattice cell. So this is for silicon lattice cell, unit cell, where the lattice constant is 5.43 angstroms. As shown here, and we calculated density of the lattice density of atoms in the lattice cell. So this unit cell has 8 atoms, 8 at 8 corners, 6 at the faces of the cube, and 4 in the middle, which are not shared. So total 8 atoms in one unit cell effectively. And lattice constant is 5.43 angstroms. So density of uh, atoms is 8 upon 1.6 into 21 minus 22. That is the volume. Volume is a cube. So density was something like this. So we can calculate density for any lattice unit cell like this. And then we have more questions on this de Broglie's wavelength and energies. Again, for this was for an infinite potential, while the energy is for free electron, the energy was h square k square by 2n. But for uh, infinite potential, well, it is n square pi square s square by 2ml square. And something about superconducting materials, electron hole pair generation. When we talk about germanium with an energy band gap and sapphire, so about transmission, electron, which wavelength is transparent. So the light's wavelength should be, the light's energy should be more than the band gap of the material for it to um, excite and generate electron hole pair, as it will be transmitted as it is, so it will be transparent to that wavelength. Then we discussed the question of indirect and direct bandgap semiconductors. Then again, question on de Broglie's wavelength. So this was all we discussed in week 1. So let us have a look at week 2. In week 2, we looked at the carrier properties, intrinsic carrier density, Fermi level, donor acceptor impurities, Fermi level in extrinsic semiconductor, the temperature dependence of carrier density, generation and recombination of carriers. And this Fermi direct statistics is very important. So please pay special attention to this as well as the temperature dependence of carrier density. So in this week, we look at the lecture notes. We started with simple questions on the doping and type P-type dopants. In the next question, we saw law of mass action, that is MP equals to Ni square, which is a very important fundamental law, valid only in equilibrium law. So please keep that in mind. Next, we looked at the resistivities, their dependence on Ni and their temperature dependence. So at different temperature, how the resistivities are changing. Semiconductor boron is P-type dopant. So how does Fermi level shift compared to undoped silicon? So this is given by EI minus EQF KT by QL and NA by NI. This comes from the Fermi direct statistics. Here KTV is the thermal energy at room temperature. It is 26 milli-electron volts. So 0.026 we replace here. Na by Ni is given 1.5 into 10 to the power 10. So you get EI minus EF, that is the shift in the Fermi level. So Fermi level shifts downwards towards EV by 0.325 electron volt. Next, we looked at the band diagram. So this is very, very important topic. You can study very well in band diagrams. How with doping, the Fermi level is changing. Then there's question of mobility. It's a gate exam question. We should practice all gate exam questions. So that is on effective masses. So EF minus E mid gap is 3 by 4 KTL and MH upon ME. The position of Fermi level from mid band gap, where does it lie? So it depends on both MEM and MH. But generally MH is larger than ME. Mobility changes with doping. Very interesting question again. And again shifted in Fermi level with doping. How does that change? Doping concentration with temperature. So this we have discussed last week also, as someone asked me in a doubt. So doping concentration, Ni, intrinsic doping, the intrinsic concentration versus T. So first is the freeze out zone with there is partial ionization. So there's the temperature is very low. So there still needs to be some ionization, some energy, thermal energy for ionization, so that complete ionization is there after some certain temperature. After there is ionization in the extrinsic region, the doping is almost constant until temperature is so high that Ni is more than the ND. Then again the device becomes intrinsic, even though you're doped, but Ni becomes more than ND. So N equals to Ni. This is the intrinsic zone. This is very important. So in the third week, we looked at these topics. Okay, so in this week we have looked at thermal motion of carriers in the electric field, mobility, drift current, diffusion of carriers. This is very important, mobility, drift current, and diffusion. And semiconductor electric energy bands, very important. So like this is the derivations from Poisson's equation and minority carrier diffusion equation, very important. This is the subset of continuity equation. The diffusion lengths. The minority diffusion length of P is in N-type semiconductor, and then the minority diffusion length of electrons is in P-type semiconductor. Don't get confused, it is opposite. The questions in this season were about Einstein's relation, d upon mu is kT by q, the internal electric field. Electric field is 1 by q del EC by del x. So you can tell the direction of electric field just by looking at the band diagram, how EC is changing with position. So the rising edge of EC is the direction of electric field. And some question on, again, diffusion length. Next, we have again question on electric field. kT by q is 1 by n del n by del x. This is from here. Here minus ei is kT by q ln n by ni. So del ei by del x is this. So E is 1 by q, 1 by n del n by del x. Another question on the same formula. Number one, you take linear slope of EC or EI or EV because all have same slope. And then question on the drift current. Drift current is NQ mu V. Einstein's relation dn by dm is kT by q. Diffusion current is minus q dn del n by del x or plus q dp del p by del x in p type. The total current is drift current plus diffusion current. And p is I square. This is law of mass action again. Then diffusion length for p type, it will be ln under root dn tau 1 Okay, this was about week 3. In week 4, we have looked at these topics. In this week, we looked at PN junctions, very important. So, signal free chart, depletion approximation, electric field at the junction, built-in potential, step junction versus linearly rated junction, energy band diagram of PN junction at quasi-Fermi levels. So this is just a derivation of PN junction using uh, the Poisson's equation, determine electric field and the built-in potential as well as the depletion width. So I would recommend you take this by heart. It's very important. Then we have different kinds of junctions: step junction, one-sided junction, graded and abrupt junctions, linearly graded junction. So for all of these profiles, the electric field profile is given. So it's easy to deduce from these charge diagrams since electric field is just integration of these charge profiles. Depletion, space charge region, electrostatics, derivation. We started with again question on doping. Next, the important concept in the depletion region extends more in the lightly doped side compared to the heavy load doped side. And charge configuration of PN junction corresponding to this PM diagram. So it will be obviously this one. And the electric field profile for the same. The next questions we looked at the built-in voltage in PN junction. This is PT by QLN and ND by NS square. The total depletion width to epsilon VBI by Q, Na plus ND upon Na and D. Again, matching the charge profile with electric fields. With simple integrations, integration of step is linear, linear is quadratic, and zero is constant. Question with in impulse charge, how the electric field would look like. So there will be a discontinuity, not discontinuity, but yeah, abrupt change in the electric field because of this impulse charge. Then again, more questions about depletion region, determining charge from depletion region, charge on the P side. PP plus junction. So this equation is not valid anymore for BBI and PP plus junction. It is only for PN. For PP plus, you need to evaluate from EF minus EI, the difference of this EF minus EI on both the sides. So we'll give you VBI. So in this case, it comes out to be KT by Q ln Na 2 by Na1. Whereas in PN junction, it is KT by Q ln Na and D by Na square. And this was all about week 4. Very, very important lecture. These were the topics in week 5. Week 5 includes PN junction under applied bias, the minority carrying junction, spatial variation in depletion and quasi-neutral regions, bend bending, and the ideal diode equation. So we started with the equilibrium and P and A squared will how in the non-equilibrium solution when you have an applied bias, how this law of mass action changes to NP equals to NA square exponential QVA by KT, where V is the applied potential, like this is the forward bias. So what VA does is reduce this potential barrier between the P and N side. Then we have the derivation for the current equation. The total current is D1 upon NA length of dP upon NDFB times Q exponential E to power QVA by KT minus 1. And this first part is the reverse saturation current. And the width of the depletion region. How we earlier we just had this VBI term with applied bias and reverse bias. This VR is added, so depletion region width is increased in the reverse bias, and the junction capacitance associated with the current derivations. Very important. Minority hole diffusion, minority electron diffusion. These are the main current components. Diffusion capacitance. How CJ varies with VBI and VR. In law of mass action. Then using what is happening in this picture. Minority carrier diffusion is given. How with temperature the reverse current changes, it doubles for every 10-degree rise in temperature. Is due to the Js dependence on Ni square and its dependence on Tq and Ag by Kt. Current density calculation, reverse saturation current density, breakdown, avalanche and Zener. Avalanche has impact direction and Zener has tunneling. Zener only happens in very high dose PN junctions. And reverse bias saturation current and relation with temperature. We know it doubles for every 10 degrees. Non-ideal diode, different slopes, high level injection, and recombination in generation, recombination in depletion region. In the coming week, we look with a more closer look at the diode non-ideal levels, breakdown, depletion and diffusion capacitance, pin diode, metal semiconductor junctions. So here we are looking at metal semiconductor junction. Does work function, electron affinity, Schottky barrier, built-in voltage, space charge region. Then some introduction to MOS capacitor, wide band accumulation, depletion, and inversion. Some more details in the metal semiconductor junction. This is the Schottky barrier. 5 bn. Opening versus rectifying contacts. MOS capacitor B6. Ideal MOS capacitor. In biasing, depletion, accumulation, and inversion. In the source of inversion charge. First question is about the depletion region in Schottky. Well, how does it change? In reverse bias, avoidance, electric field versus position in a metal semiconductor diode. EF minus ER is KT by QL and ND by NI. Then we are trying to calculate phi B. Phi B is QVBI plus EC minus ES. We calculate EC minus EF from here and VBI from here. VBI is the area under this electric field curve. Then phi B is just QVBI plus EC minus EF, which is 0.62 electron volts. Phi M is, so phi B is phi M minus chi. Phi B is phi M minus chi. Plus phi M. This is chi, so this is phi B. Phi B is phi M minus chi. So from here we can calculate phi M. Then about question about MOS capacitor, flat band condition, bands are flat. Again, question on phi B is phi minus chi. Phi B is also QVBI plus EC minus EF. Phi B is phi M minus chi. equations, inversion, depletion. So this is a bounce gap. This is P type. This is N type. This is N type. Based on this EF and EV level. So this is P type semiconductor. So this is NMOS cap. This is N type semiconductor. This is PMOS cap and PMOS cap. So this is depletion here. This is inversion. This is depletion. This is overnick. This is short key. This is PN. This is all about week 6. In the next week, we looked at the ideal MOS capacitor, qualitative analysis of field effect, block charge, electric field, potential diagrams, energy band diagrams, accumulation and inversion regimes, gate voltage drop across MOS capacitor, MOS device. Yeah, so we are in week 7. So we looked at the energy band diagrams of MOS capacitor and MOS accumulation. How is the charge in that case? We have positive holes here because this band diagram becomes closer to here. So we have positive holes accumulation here. In depletion, electrons are accumulated here. This is the surface potential. In inversion, we have more electrons here, and this is the inversion part. Here, EF is closer to EC than, whereas in bulk, EF is closer to EV. So this is the inversion condition where it is inverted. And the electrons, inverted electrons is equal to the background doping. That is this difference between EI minus EF is same as this difference EI minus EF. This phi F is same as this phi F. That is the inversion condition. Or that voltage is called a threshold voltage. So VG is Vox plus psi S. So some voltage drops on in the oxide and some in here in the psi S. And VG Vox is minus UD by Cox. This comes from here. Pox is epsilon or Tox is epsilon S I epsilon as ASI by Ox. Q and W by epsilon S I. Just replacing these, this we get this QD by Cox. In band diagram and block charge. Surface potential, gate bias. Threshold when surface inversion charge is equal to bulk doping. Psi S is equals to 2 phi F. Now psi S changes with the charge, semiconductor charge changes with Q. It is exponential in accumulation and inversion and square root dependence in depletion. So till 0 to 5F, it is the soul is depletion, but it is like weak inversion. And after 2 5F, it is strong inversion. 2 5F is the case where we have threshold voltage. Questions on this charge versus size. environment condition. Okay, equivalent diagram of capacitance. We have oxide capacitance and the depletion capacitance. Thickness of a SiO2 layer is typically 1 to 2 nanometers. Threshold voltage is this QD by C of plus 2 phi f. In this QD we have 2 phi f. So essentially it is under 2 epsilon QNA 2 phi f by C of plus 2 phi f. This is the threshold voltage. And pi f is KT by QLN and NA by NA. That is the difference between Fermi level and intrinsic energy mid band gap. EF and EI due to the doping NA. There's a question about COX and depletion capacitance. Question about fiber. Gate voltage, doping, flat band voltage. Flat band voltage is the voltage when bands are flat. Yes, pi psi s is 0. WD maximum depletion width is that when psi s is 2 phi n, that is the end of depletion. So WD is under 2 epsilon si psi s by QNA with 2 epsilon si 2 phi f by QNA. So this was all for week 7. In week 8, we looked at threshold voltage of mouse device, CV measurements, high frequency, low frequency, and non-identities. The function difference, flat band voltage, tunneling over gate barrier, leakage current, high K dielectrics. Work function difference, phi ms is not 0, then your device will be in the starting either in accumulation or in depletion. So VT changes like this phi ms minus QD by CS plus 2 phi f. Earlier we had only this. Now we have this phi ms term also. So if phi ms is higher, if phi m is greater than phi s, the VT will increase. That means device will be in accumulation at start, and if phi m is less than phi s, device will be in depletion at the start, and your VT will decrease. Then what different type of polysilicon gate can give a different type of VT conditions. Mass CB characteristics. So in high frequency, you have this. You don't go to this again at top because the charges they don't react. So the charges don't react to the charges and they are generated thermally. It's a slow curve. They don't react to high frequency changes in charge. So it stays down. Doping and oxide thickness they condense as Na increase. Your VT increases and this also increases. As Tox increase, VT reduces. VT increases with Tox actually. So there is no label here, but yeah, VT increases with Tox. With temperature also. depletion gap increases. Segment first is about low frequency and high frequency CV. Then about next question about equivalent oxide thickness. When you have high grade electric, so it has a higher epsilon, higher permittivity. What would be its equivalent thickness in SiO2 terms? So that is calculated by this T high K is epsilon high K into T SiO2 epsilon SiO2. So this relation holds everything. Then again question on maximum depletion width, question on C ox and C depletion. Which condition is which? Fourth is flat band, 5 is accumulation, 3 is depletion, 2 is threshold, 1 is inversion. So this is a PMOS device. So it is opposite. So accumulation is in positive voltage and depletion and inversion in negative voltage. So it is a PMOS device. This is an NMOS device. What is the doping dependence? Highest doping will have higher depletion capacitance because WD is 2 epsilon psi s by Q Na. If Na increases, WD will decrease. And if WD decreases, CD will increase. Have to calculate gate oxide thickness from CV information. Very important question. How TOX affects CV. TOX will increase, your threshold voltage will increase. COX will also decrease. Phi mf calculation and VT calculation and charge calculation, fixed charge. In the 9th week, we looked at long channel MOSFET, its qualitative understanding IDVG. Pinch off, inversion charge, gradual channel approximation, the current characteristics, linear current, saturation current, body effect, output characteristics, transfer characteristics, subthreshold swing, CMOS inverter. Current equations. Again, question on current, overdrive voltage, VG minus VT, subthreshold swing is defined as change in gate voltage delta V by for decade change in current. The subthreshold swing limit 60 millivolt per decade and KT by Q 2.303. 6.026 and is ideally 1. 60 millivolt per decade is the minimum and is only more than 1. Channel length modulation increases output conductance, reduces output resistance. Saturation condition, pinch off, mobility versus electric field, velocity, saturation, body effect coefficient to Q epsilon SINA by COX. CMOS questions. Then week was the last week for MOSFET. Here we talked about scaling, short channel effects, velocity saturation, channel length modulation, debulk, IV characteristics in long and short channel MOSFETs, overview of FETs, FinFET, tunnel FET, nanowire FET, MOSFET scaling, that is Dennard scaling, 1.7 scaling, also called as everything is changed to 0.7 times. So reduces area by 50%, capacitance by 30%, gate capacitance by 40%, current 30%, delay 30%, power 50%. Talking about the scaling in MOSFETs, smaller than RBC, long channel, short channels, deviation from square law theory due to velocity saturation. So this locus is quadratic in long channel MOSFET, whereas it is linear in short channel MOSFET. Channel length modulation, you cannot ignore this depletion due to drain side. So your current equation is modified 1 plus lambda VDS. This gradient is dependence. Mobility degradation due to surface roughness scattering. Threshold voltage reduction due to charge sharing. Narrow channel effect, Dibble, how drain voltage is impressing the barrier at the source and gate source channel side. Reducing this barrier is lowering BT even without or reducing charges in the channel without applying any gate potential. So just by your drain voltage, your channel is being controlled, which is undesired. The drain induced barrier loading. Drain is inducing the lowering of barrier between the channel and source, which brings in the electrons to the channel. It is seen like a parallel shift in short channel effects. In short channel MOSFETs, or high VD and low VD is a parallel shift, rather than long channel MOSFET. As a threshold region is similar almost. No VD dependence. Here it is VD dependence. And modern transistors, high stress, high chemical rate, trainer to FinFETs, then FinFET to nanosheet FETs. Here we have question on scaling, power dissipation, velocity saturation, Dibble, narrow channel effect, and silicon mobility improvement, EOT, effective oxide thickness, FinFETs, delay reduction, scaling questions, velocity saturation again. So all about MOSFET. So mainly last 2 weeks are on optoelectronics. We have just seen it, so I won't go through the summary there on the assignments. But mainly some helpful tips for your exams is you solve all assignments as well as previous year assignments. Solve the live session questions as also very thoroughly. So many questions are repeated in the exam directly from the assignments or previous year assignments. And we are also, the TAs are also solving previous year exam assignments. So many of the questions, almost 20-30%, you can see it as it is taken from assignments, and many more, up to maybe 50-60% can be just your assignment or previous year assignment questions with just changes in values. So if you just solve your assignments diligently and watch the videos, you can pass the course, pass the examination. But to do well, solve also there are many solved examples taught by professor in the lectures. So you should see those lectures very well. And also doing gate questions will help you with your gate examination also. But there are also in some assignments some gate questions from previous years. Key topics are semiconductor doping, Fermi statistics, depth diffusion, then PN junctions in the band diagram, electrostatics, current and breakdown, Zener and avalanche breakdown, drift diffusion current, reverse bias, forward bias in MOS band diagram, operation, region of operation, accumulation, inversion, depletion, CV characteristics, low frequency CV, high frequency CV. In MOSFET, your band diagram again, operation, accumulation, inversion, depletion, surface, um, potential, IV, CV, changes in IV and CV due to uh, threshold voltage, changes in IV and CV due to doping or uh, scaling, oxide thickness, body bias, subthreshold swing, then short circuit effects, barrier reduced, barrier lowering, threshold swing degradation, velocity saturation, channel length modulation. All these are very important, not just for the sport, but for your professional career and also. MOSFET is the most important topic in whole semiconductor physics. Every circuit is based on MOSFET. Okay, so this was all from this lecture, summary lecture. If you have any doubts, please feel free to email me. And this was the last live session for this course. I wish you all the best for your exams. Thank you so much.